This is a video from section 16.2. The directions say to evaluate the line integral where c is the given plane curve. On number 1, we have the integral over c of y ds, where c is the curve given by the parametric equations x equals t squared, y equals 2t, where t is greater than or equal to 0 and less than or equal to 3. So dx dt is equal to 2t, and dy dt is equal to 2. We're going to need that in order to calculate ds, to find ds. Now, ds is the square root of dx dt squared plus dy dt squared dt. Now, notice dx dt squared is 2t quantity squared. Dy dt squared is 2 squared. So we have ds is the square root of 4t squared plus 4 dt. Now, when we make our substitution, the integral over c of y ds is the integral from 0 to 3. Why? Because t goes from 0 to 3. So we have the integral from 0 to 3 of 2t times the square root of 4t squared plus 4 dt. And from here, we're going to take the integral from 0 to 3 of 2t times the square root of 4 times the quantity t squared plus 1 dt. But remember, the square root of 4 is 2. 2 times 2 is 4. So this is the integral from 0 to 3 of 4t times the square root of t squared plus 1 dt. And so this is a u substitution problem. So I'm going to let u equal t squared plus 1. Du is 2t dt. So t dt is 1/2 du. But remember that our limits of integration are in terms of t, and we want to transform them in terms of u. So when t is 0, I'm going to plug that in up here and get u equals 1. And when t is 3, u is 10, because 3 squared plus 1 is 10, right? So I'm going to get 1/2 times 4 times the integral from 1 to 10 of square root of u du, right? And the 4 just came from that constant right there. And so 1/2 of 4 is 2. And so I get the integral from 1 to 10 of square root of u du. And again, we have that 2 on the outside. So this is 2 times 2/3 u to the 3/2, evaluated from 1 to 10. And so if I plug the 10 in, remember, 10 to the 3/2 is equivalent to 10 times the square root of 10. Okay? So I get 4/3 times the quantity, 10 times the square root of 10, minus, and when I plug 1 in for u, 1 to the 3/2 is 1, so I just subtract 1. And that's my answer. On number 2, we have the integral over c of x over y ds. And c is the curve given by the parametric equations x equals t cubed, y equals t to the 4th, where t is greater than or equal to 1 and less than or equal to 2. dx dt is 3t squared, dy dt is 4t cubed. So ds, right, we need to get our ds, and you're going to see in every one of these, I'm going to get ds first. So ds is the square root of 3t squared quantity squared plus 4t cubed quantity squared dt. So this is the square root of 9t to the 4th plus 16t to the 6th dt. So if I factor out a t to the 4th inside the radical, I get t to the 4th times 9 plus 16t squared under the square root dt. But the square root of t to the 4th is t squared. So this is equal to t squared times the square root of 9 plus 16t squared. Now, this is substitution. So if you notice, I'm going to take the integral over c of x over y ds. But remember that t goes from 1 to 2, right here. So t goes from 1 to 2, so I'm integrating from 1 to 2 of x is t cubed, divided by y, which is t to the fourth, and I'm going to replace ds with t squared times the square root of 9 plus 16t squared dt. But t to the third over t to the fourth times t squared is just t. So this is equal to the integral from 1 to 2 of t times the square root of 9 plus 16t squared dt. Again, another u substitution. I'm going to let u be 9 plus 16t squared. Du is 32t dt. So t dt is 1 over 32 du, right there. When t is 1, u is 25, right? Because 16 times 1 plus 9 is 25. When t is 2, 2 squared is 4. 4 times 16 is 64. 64 plus 9 is 73. So I get the integral over c of x over y ds is 1 over 32 times the integral from 25 to 73 of square root of u du. So this is 1/3 times 2/3 u to the 3 halves. Okay, evaluated from 25 to 73. So when I plug that in, I get 1 over 48 times the quantity, 73 root 73 minus 125. And that's the answer to number 2. Number 3, suppose I have the integral over c of x y to the fourth ds, where c is the right half of the circle x squared, x to the second, plus y to the second is 16. And so to parameterize a circle like that, remember that cosine squared t plus sine squared t is equal to 1, right? But the radius of that semicircle is 4. So I'm just going to multiply cosine t by 4 for the x coordinate, if you will, and the y coordinate. So here I'm going to have x equals 4 cosine t and y equals 4 sine t, and I'm going to take t to be between negative pi over 2 and pi over 2. And I can make a video on how to parameterize different curves, but that's how you would parameterize the right half of a semicircle. So dx dt is negative 4 sine t, and dy dt is equal to 4 cosine t. So ds, right? So we need our ds right here, is going to be the square root of 16 sine squared t plus 16 cosine squared t. But that says ds is 4 dt. And so let's make sure we're okay there. So ds is the square root of 16 times sine squared t plus cosine squared t dt. But remember that sine squared t plus cosine squared t is 1. And the square root of 16 is equal to 4. And so that's where I'm getting ds is 4 dt. Now it's just a substitution game. I'm going to come over here and I'm going to take the integral over c of x y to the fourth ds, which is the integral from negative pi over 2 to pi over 2. X is 4 cosine t. Y is 4 sine t. So I'm going to take 4 cosine t times 4 sine t to the fourth, right? ds is 4 dt. So I take that quantity and multiply by 4 dt. Now, let's get to this line. So remember, I have 4 to the fourth times 4 times 4. but that's just 4 to the 6th. So I have 4 to the 6th times the integral from negative pi over 2 to pi over 2 of cosine t times sine to the 4th t dt. But remember that the derivative of sine t is cosine t. So to get from here to here, think about just integrating u to the 4th du. U to the 4th du is, to integrate that would be 1/5 u to the 5th, right? From one limit to another. Well, so we're working backwards. And so here I get 4 to the 6th times 1/5 sine to the 5th t evaluated from negative pi over 2 to pi over 2. And that's just a matter of plugging it in. So I get 4 to the 6th times the quantity. If I plug the pi over 2 in, I get sine of pi over 2 is 1. So I get 1/5. And then I'm going to subtract negative 1/5. Now, why is that? Because remember, sine of negative pi over 2 is negative 1. And so this is 4 to the 6th times 2/5. And that's basically what I get here. I get 4 to the 6th times 2 divided by 5. And that would be the answer for number 3. If we take a look at number 4, we get the integral over c of x e to the y ds, where c is the line segment, from 20 to 54. Now, this parameterization for a line segment, it only works for line segments, so you want to be really careful here. So to parameterize a line segment, we're going to take x, y, the ordered pair, and we're going to take 1 minus t times 20, so that's the first point, and we're going to add t times the second point, 54. And t is restricted between 0 and 1. And I want you to observe something. Notice, when t is 0, if I plug 0 in for t, this piece goes away, and I get essentially 1 times 20. So my xy would be 20. And then when t is 1, then this first ordered pair goes away, and I plug 1 in for t, and my xy would be 54. So I get the last point. And I claim when you plug in any value between 0 and 1, you're going to get all the points between 20 and 54. So this is how you parameterize a line segment. You take 1 minus t times the first point, and then you add t times the second point, and you just restrict t between 0 and 1. Are there other ways to parameterize that line segment? Yes, there are, but this is a pretty good way to parameterize a line segment. So I'm going to show it this way. Now, x is going to be 2 times 1 minus t plus 5t, which is equal to 2 plus 3t, and y is equal to 4t. And so once again, we're going to need ds. So dx dt is 3, dy dt is 4. So ds is 5 dt. And so we're going to take the integral over c of x e to the y ds. Now, I'm going to replace x with 2 plus 3t. I'm going to replace y with 4t, right? That's up here. So I get the integral from 0 to 1 of 2 plus 3t times e to the 4t. ds is 5 dt. So it's all substitution all the time, okay? Now, I'm going to distribute that 5 in, and so I get the integral from 0 to 1 of 10 plus 15t times e to the 4t dt, and I'm integrating from 0 to 1. So this is classic integration by parts. So I'm going to let u be 10 plus 15t. du is 15 dt. dv is e to the 4t dt. And then v is 1/4 e to the 4t. So I'm going to take uv minus the integral of v du. So, right, uv minus the integral of v du. So I think about it like a zigzag. And that's what I did over here. So I take 1/4 of 10 plus 15t times e to the 4t evaluated from 0 to 1 minus 15 over 4 times the integral from 0 to 1 of e to the 4t dt. So if I plug the 1 in for t, I get 25 over 4 e to the 4th minus 10 fourths minus 15 fourths times the quantity. And remember, the integral of e to the 4t dt is 1/4 e to the 4t. So I'm going to evaluate that from 0 to 1. And if you notice, I took 15 over 4 times a fourth. So I get 25 e to the 4th minus 10 over 4 minus 15 sixteenths. And then, again, plug 1 in for t, I get e to the 4th. Plug 0 in for t, e to the 0 is 1. So I get minus 15 sixteenths times the quantity e to the 4th minus 1. And so I just did some arithmetic here, if you will, and got common denominators and everything. And at the end, I got 85 e to the 4th minus 25 over 16 when I was done. That was number 4. Okay, now we're going to look at a slightly different problem. On number 5, we're going to take the integral over c of x squared y plus sine of x dy. So once again, this is all substitution. C is the arc of the parabola y equals x squared from the ordered pair 0, 0 to the ordered pair pi, pi squared. And so now, if y is a function of x, so I made x my parameter, if that makes sense. Now, I could have used t or something different. I just chose to use x. So I'm going to express y in terms of x. And then one thing I want to note on this problem, remember that x is greater than or equal to 0 and less than or equal to pi. Why? Because again, I'm going from the ordered pair 0, 0 to the ordered pair pi, pi squared. Okay? So I'm going to take the integral over c of x squared y plus sine of x dy. And that's the integral from 0 to pi of x squared times x squared plus sine of x times 2x dx, right? And that 2x dx came from here. Remember, if y equals x squared, dy is 2x dx. Just like regular substitution. And that's what I have here. And so I'm going to take the integral from 0 to pi of, now x squared times x squared is x to the 4th. X to the 4th times 2x is 2x to the 5th. So I broke up this integral. So I have that integral. And then I'm going to take the integral from 0 to pi of 2x dx. And so on the next couple pages, I evaluate each integral separately. So if you notice over here, the integral from 0 to pi of 2x to the 5th dx is pi to the 6th over 3. And then the integral from 0 to pi of 2x sine x dx requires integration by parts. So I'm going to let u equal 2x, du is 2 dx, dv is sine x dx, and then v is negative cosine x. So remember, it's uv, which is negative 2x cosine x, evaluated from 0 to pi, minus the integral of v du, which ends up being plus the integral from 0 to pi of 2 cosine x dx. And so I end up getting negative 2 pi cosine pi plus 2 sine x evaluated from 0 to pi. And so the answer there is just 2 pi. And I'm done, because I'm going to take the 2 pi and then I'm going to add pi to the 6 over 3 to my final answer. And so the integral from 0 to pi of x to the 4th sine x, that quantity times 2x dx, is pi to the 6 over 3 plus 2 pi. That's the answer to number 5. And then our last example for this video, we have the integral over c of e to the x dx, where c is the arc of the curve, x equals y cubed from -1 to 1, 1. So notice how x is a function of y. So the way you parameterize a curve like that is I'm going to set y equal to t. But that says x equals t cubed, right? And t goes from -1 to 1, right? Because remember, y is from -1 to 1, but y is equal to t. So t goes from -1 to 1. But remember that we need dx here. So dx is 3t squared dt. And remember, this is all substitution all the time. So I'm going to take the integral from -1 to 1 of e to the t cubed times 3t squared dt. But that's e to the t cubed evaluated from -1 to 1. If I plug 1 in for t, I get e. If I plug -1 in for t, I get e to the -1. So my final answer is e minus e to the -1. And that's going to conclude this video for section 16.2. And we did line integrals, problems 1 through 6 in the Stewart calculus textbook. Okay, thank you.